Hi, everybody. Welcome to our Physics 2 lab final exam review session. What I'm going to do today is just walk through the most commonly missed quiz questions and then open it up for you guys to ask questions if you have them. If you would like to go through kind of a summary of the experiments, that's fine. I know some people had requested going through error propagation and the calculations that we have done, but I think you'll find that we'll cover that through the most commonly missed quiz questions. So if you have any questions, feel free to ask. Of course, if you're watching this recording, feel free to send me an email and I will do the best I can to answer you via email. Or if it's a lot of questions or they're really complicated, we can potentially set up a one-on-one session after this. So let me go ahead and share my screen and we'll get going. All right, can you guys all see my PowerPoint?
Yep.
Perfect, thank you. Okay, well, here we go, final exam review session. Okay, so again, I'm gonna cover the most commonly missed quiz questions, but I want you to keep in mind that each quiz question has about 4 or 5 versions to it. And so I'm not gonna cover every version of every question on every quiz, but I do think that I hit every type of question except for the ones that most people got correct, or the ones that were really just rereading the theory section in the manual, just for the sake of time. So most of the questions that we're going through today are the calculation-based and some of the conceptual-based questions if many people missed them. All right, so quiz 1, we had experiments 1 through 3 covered on this quiz. So that was electrostatics, electric field mapping, and capacitors. Those were what we covered on quiz 1. So for this first question that students missed, we had the Faraday cage, which you should recognize. It was used in the electrostatics experiment, so experiment 1. There's an electrometer connected to the inner cylinder, and then the outer cylinder was grounded. So what we did for this experiment, we rubbed wands together, and then we kind of dipped them into that middle cylinder and saw whether the electrometer read positive or negative or 0. So when we rub the wands together, what happens is that one of them kind of rips electrons off the other one. So the one that has extra electrons ends up being negatively charged, and the one that loses electrons is positively charged. So if we put the positively charged wand inside that inner cylinder and then touch the cylinder and remove it from the cage, what happens is that we end up with kind of a small net positive charge inside the cage that the electrometer will then read as a small positive number of volts. Any questions about this question? I think the most common answer that I saw for this one was 0, which would not be the case since we're specifically touching the cylinder.
Hey, phone. Can they screenshot when you?
Can you screenshot? Was that a question directed to me?
No, sorry, my bad.
Okay. Okay, and I'll also, just so you guys know, I'll also post this PowerPoint on Canvas so you can go through these at your own pace. All right, next question. Again, from the electrostatics experiment. Again, we rubbed those 2 wands together. The white one, the blue one, rub them together, and then we separate them and put them into the cage separated. And we see 6 volts. I'm sorry, the white wand is put in the cage, and we see positive 6 volts. So this problem, I suppose you could say, happened a lot in Florida, where the room air was very humid. And so he's asking, since it's so humid, what is the most likely approximate reading of the electrometer when wand B is also placed inside the Faraday cage alongside but not touching wand W. So now at first, the positive wand is dipped in there and we get a positive reading. And now we're also putting that negative wand in there. If this were a dry environment, so not Florida, what would we expect the reading to be when both of them are in the cage? Hopefully you can answer that in your own head. We should expect 0, right? And so that was the most common answer for this question as well, that the two net charges would kind of cancel each other out and we'd end up with a net charge of 0. But since the air in the room is humid, that means it's kind of stealing the electrons off of that blue wand. It's dissipating the charge very quickly. And so we end up with more positive than negative because the humidity has taken away some of those negative charges. And so we end up with a small positive net charge. So +1 to +4 volts. I'm sorry. Any questions about this question? Okie dokie. The next one is very similar, except in this case, instead of putting them both into that bucket together, we're removing that positive wand and now dipping that blue wand, the negative wand, into the cage. Same idea though, the humidity in the air is taking away some of the electrons off of that negatively charged blue wand. And so we end up with a smaller negative charge than we would expect. Right? We would expect to have -6 because you've rubbed them together. Conservation of charge says they should be oppositely charged but the same magnitude. And yet we have this humidity that makes the system not closed. So the humidity is stealing away some of that charge. Same scenario, but this time we're in a very dry room. Ha, not in Florida. And so he wants to know what is the most likely approximate reading when both of them are placed inside the cage together. And of course, the answer to that would be 0. Due to conservation of charge, that means the total net charge in the system would be conserved. So +6, -6 equals 0. I think that's the last one about this particular scenario. So again, if you guys have questions, feel free to stop me at any time. I'm trying to monitor the chat, but I can't have both the chat window and my PowerPoint open at the same time. So if I don't see your question, just let me know. Okay, so this question pertains to experiment 2. Electric field is equivalent to the Coulomb force divided by the amount of charge on the object creating the electric field. And that's really the key phrase right there, the object creating the electric field. That's what makes this question false. Okay, we can see from our equations that electric field does equal force over charge, but it's not the charge of the object creating the field, it's the charge of the test charge, or the second object in the scenario. So this was kind of a tricky question. I found that a lot of his questions tend to be, you have to make sure you read the question carefully. Otherwise, it's pretty easy to just assume that you know the scenario and it's actually something different. So be careful of those sorts of questions. Make sure you read them very carefully. I know you're under time pressure in an exam, but don't let that trip you up. All right, next question pertains to experiment 3. Calculate the charge stored in microcoulombs, and then use consistent significant digits in the answer. So we can see in the picture down there that each value has 3 sig figs. And then Canvas, just automatically adds these zeros when it posts the correct answer. But the answer that he was looking for was just 348 because that's also 3 sig figs. So here's the way that we figure this out, right? We can see it in our circuit diagram that there are 2 parallel branches, but then that first branch has two capacitors in series within that branch. And capacitors in series and capacitors in parallel add together differently to find the total capacitance. So when we're dealing with a parallel circuit, the capacitance, the total capacitance is just C1 plus C2. So branch 1 plus branch 2. Branch 2, that one to the right, is easy to figure out because the total capacitance there is just 17.8 microfarads. However, that middle branch, branch 1, it's a little bit more complicated to figure out the total capacitance there because they're in series. So we have to remember, when we have capacitors in series, the equation is 1 over total capacitance equals 1 over C1 plus 1 over C2. And so just for the sake of nice formatting in this example, I just put 1 over C1 plus 1 over C2 to the inverse, so the negative 1. But it's the same thing. So that's how we calculate it, right? 1 over C1 plus 1 over C2, the inverse of that, plus C3 gives us our total capacitance in microfarads, so 29 microfarads. But that's not what he asked for. He asked for the total charge. So we need to remember from equation 3.1 in the manual that capacitance is charge over our potential difference. So charge is capacitance times potential difference, or times our voltage. So 29 microfarads times 12 volts gives us 348 microcoulombs. So again, these numbers might not correspond to your version of the question, but hopefully you can follow this reasoning on your own quiz and see what answer you should have gotten there. Do you guys have any questions about this one? This was a really commonly missed question. We may find as we go through these questions that you understand them better now than you did when you were actually taking this quiz. I hope that's the case. That's a really good sign. So if some of these questions seem very straightforward to you now, that's a good sign for you. If they don't, that's okay. But I definitely recommend that you take some time and rework your quiz problems yourself to try to get to the right answer. Again, following these as a guide. All right, next question. This pertains mostly to like experiment 2, potentially a little bit of experiment 3, but just experiments in general. Often we initially connect a wire from the DC power supply's red jack to its black jack, and then increase the voltage slightly. And then we decrease the current knob all the way down to basically 0, or often he had us at 0.3 amps. And the question was, why do we do this? And the reason is so that we don't blow the fuses in our whatever equipment we have plugged in, right? If the previous experiment was set to a really, really high current, like some of them were, and then we leave it like that, and the next group comes in and doesn't kind of recalibrate it like this, then they plug in some like one of those little flimsy light bulbs. Well, that's going to pretty much explode the light bulb, which would be very exciting, but not ideal. And it could just damage the equipment. So we turn the current all the way down. And then once we have everything set up in our circuit, then we start increasing it to whatever our desired value is. All right, what is the purpose of touching the uninsulated ends of a wire to the opposite legs of a charged capacitor? So if you picture a capacitor in your mind, it's got that like little middle cylinder, and then it has the wires sticking out of either side. So when we take our wires and kind of touch them to those capacitor wires, what it does is kind of removes any previous excess charge that may have been stored there from an earlier group's experiment. So that's called grounding it. And it's really important that we do that so that we know our results are calibrated. And if not, then that introduces some systematic error in measurement that is problematic. All right. This pertains to experiment 2. A movable negatively charged particle will tend to move from a region of high electric potential to a region of low electric potential. And this one is false. This was another tricky one where you had to realize that he's talking about a negatively charged particle. Test particles are kind of by definition positive charges. That's just how they were defined originally. So that potential difference, that region of high potential to low potential, is the motion that a positive test charge would take. It would go from high potential to low potential, just like going down a mountain is preferred usually to going up a mountain. But these negatively charged particles behave oppositely to how positively charged particles would. So if our positive test charge goes from higher to lower, that means our negative test particle would go from lower to higher. So that was another tricky one. Make sure that you're reading carefully for those sorts of things. All right, next question pertaining to experiment 3. We have these 2 different air gap capacitors. And this question, you can see the actual question is like in the picture. What is C1 over C2? So the equation for this was kind of embedded into the procedure. You had to look sort of carefully for it. So experiment 3, part 2, step 5, there's an equation in there for the capacitance of parallel plate capacitors. So C equals epsilon of air, which is just a constant, times the area of the plate divided by the distance separating the 2 plates. And so since we have 2 different shaped plates, we have 2 different area equations. So the first one, C1, is a circle. The area of a circle is pi r squared. And in this case, the radius is a. So our area for that plate is pi a squared. And then if we look at our square, the area of a square is base times height. So 2a times 2a gives us 4a squared for that area. And now he wants to know what C1 divided by C2 is. So we set up our ratios. C1 is epsilon air times the area of the circle divided by the distance between the 2 plates for the circles. And then likewise for C2, we have epsilon air times the area of a square divided by the distance separating the squares. So epsilon air cancels out on top and bottom. Our area is pi a squared. The distance between the circles is s. And then for the square, our area is 4a squared. The distance separating them in this case is 2s. And so we can see the a squares cancel out, the s's cancel out. 4 halves simplifies to 2, so we get pi over 2, which is just 1.57. So in this question, there are several different versions. Like I know in one of them, the square plates were separated by a distance of s as opposed to 2s, that sort of thing. So go through and make sure you understand your specific geometry for your question, but it's the same setup for everything. Epsilon air will always cancel out, and just simplify it as much as you can from there. All right, so this one actually more pertains to Physics 1 lab than Physics 2 lab. This is all about classifying air, which I know you guys did in every single lab report, but sometimes it can be kind of tricky to figure out which type of error you're dealing with. So in this case, we're dealing with a multimeter, and it says, you know, we're dealing with a capacitor here. So over time, this leakage of charge from one plate to another through that insulation between them degrades the insulation, and then if you connect a multimeter to an overused capacitor like that, you would get an error in your measurement of that capacitance. And that would be an intrinsic systematic error that would result in that. It's built into the equipment itself, the capacitor itself. That's not something that you can control. So that's intrinsic. And then it's systematic because it's changing all of your measurements from that capacitor in the same way. You know, it won't spontaneously decide to repair itself halfway through your experiment. it will stay kind of damaged. So that's why it's intrinsic systematic error. All right, same kind of deal. What type of error are we dealing with? We have a multimeter there, and there, I'm pointing at my screen, but you can't see me pointing. Anyway, up in the top right corner, there's a little knob labeled ADJ. That means adjust. And so that's how we calibrate our meter. If our meter is not calibrated, it will change all of our measurements in the same way. So it's systematic, but it's something that you could fix. So that would be an error in measurement. It's not, that error is not built into the multimeter itself. Does that make sense? It's a little bit sometimes hard to see the difference between the previous example where the error is built into the capacitor and this example where the error is not built into the multimeter. But again, it's just because you can't control the capacitor, you can't fix it, but you can control this multimeter and you can fix it. So that would be a systematic error in measurement. I believe it's Appendix I in your lab manual that goes through how to figure out which types of error you're dealing with, if that's something that you need to review on your own. I will say, and I haven't looked at the exam yet, it wasn't made available to us. Well, all of the questions still aren't available to me, but I haven't had a chance to look through it yet. So I'll do that today, and I'll try to post an announcement with some helpful tips for you guys later on today. But he does generally like these questions, so make sure you're familiar with this idea. All right, this one pertained to experiment 2, mapping the electric field, electric potential. So remember in this experiment, we had that tray of water with the ring inside of it, and we gave that ring a charge to create an electric field inside. And then we had these probes that measured the potential at all of these different points inside the ring. So here are the measurements that you get from that for the potential. These numbers are in volts. And he says, suppose the points where the voltages were measured are separated by 1 centimeter in both the X and Y directions. And he wants to know what is the magnitude of the electric field at a point at the center of these data. So the center of the data, hopefully you guys can see my mouse, is like right about in there. And so if we look at equation 2.6 in our manual, it tells us that the potential difference, so the difference in potentials, is equal to the electric field times kind of the distance between them. So I chose to look at this part right here. I took that to be the center. You could have chosen this one and it would have worked the same way. But we want to find the difference in the potential here. So 3.01 minus 2.02 divided by the distance between them, which he tells us up in the question is 1 centimeter. So I converted that to meters because he wants the answer in volts per meter. And we get, I'm sorry, my unit is incorrect there. It should be volts per meter. But we get an answer of approximately 100 volts per meter for our electric field. So the answer that Canvas would accept is 100 plus or minus 5. So if you had put in 101, that would have been acceptable. I know a lot of students missed this one. Hopefully, it looks very overwhelming looking at all of those numbers, but hopefully this process makes sense. What I did here, again, electric field is just the difference in the potential divided by the distance between those points. So it ends up being a very simple calculation, even though it's very overwhelming to look at initially. All right, moving on to quiz 2 now. So this was experiments 3 through 5. Remember, he quizzed you on experiment 3 capacitors twice because I don't really know why he chose to do that. But anyway, extra practice with capacitors, I guess. So let's go through it. Two 150 plus or minus 10% microfarad capacitors are connected in parallel. Determine the propagated absolute error in the equivalent capacitance. And the answer that we're aiming for there is 21. So remember, we already kind of went through the difference between capacitors in series versus capacitors in parallel. But equation 3.7 tells us that the total capacitance is C1 plus C2 plus however many you have in parallel. In this case, it's just 2. So to find the error propagation of this, we're going to need our error propagation formulas in Appendix C. And since this C1 plus C2 is how we calculate C total, that means that we're going to be looking for the error propagation formulas that correspond to X plus Y, where X is C1 and Y is C2. So really there are 2 different methods that you could have chosen to calculate this. I do find that one of the methods is easier than the other one in this case. And in another case that I'll show you later on, it's flipped. So for this one, I'm just going to show you the easier method, which is to convert to absolute error first and then propagate those errors. So the percent error that we're given for each of our capacitors is plus or minus 10%. And they're the same capacitance, so that's convenient. So 10% of 150 is 15. And so when we look at that error propagation table in Appendix C3, and the X plus Y row, we're looking for the absolute error, so that's the middle column. And this is the equation that it shows us. So the square root of sigma x squared plus sigma y squared. In this case, both the numbers are the same. So the square root of 15 squared plus 15 squared, which is 21. So I also want to recommend that you have a calculator handy for your exam, of course, but also use the calculator. I know in a hurry, it might be tempting to just look at the square root of 15 squared plus 15 squared and say, oh, it's 15. It's not. It's not 15 because you're adding them together. It's not just the square root of 15 squared. It's the square root of 15 squared plus 15 squared. And so don't get tripped up by those simple mistakes that if you had taken the time to plug into your calculator, you would not have made those errors. So 21 is our correct answer for this. All right, next question. 823H is the label on a capacitor. A measurement of that capacitance yields 84,700 plus or minus 10 picofarads. Do these values agree statistically? And the correct answer is yes. So for questions like this, we're going to refer to Appendix F to see those color codes for resistors, capacitors, all that jazz. Again, I know Mr. Gehring sent out an email about this today, but definitely make sure you have Appendix C, Appendix F, and Appendix I handy. I would say those are going to be 3 really helpful ones. Appendix C for error propagation, Appendix F for all of your color codes and resistors and tolerances and all of that stuff. And then Appendix I to just remind yourself of things covered in Physics 1 lab if you took that a while ago. Anyway, if we look at that chart in Appendix F, we can see that H corresponds to a tolerance of plus or minus 3%. And so if we take plus or minus 3% of the label on the capacitor, then add that uncertainty onto our value. If the measured value is within that range, then yes, they do agree statistically. So we can see that clearly 84,700 is within that range. It's less than 82,300 plus 24,690. So yes, these definitely do agree statistically. And those numbers seem incredibly large compared to the measurements that we took in lab. But you have to remember that this unit is picofarads, which is times 10 to the negative 12. So these are actually very, very small capacitances, even though they seem really large. Okay, again, this chart comes from Appendix F. I just took a screenshot of it and put it in there for you. So figuring out the colored bands on a resistor, I think was experiment 4, 5. I should have put the numbers in with the slides, but I didn't, sorry. So let's see. Experiment 5 was resistors in series and parallel. Experiment 4 was Ohm's law. So yeah, this corresponded with, I guess, both of them actually. And so given those colored bands on the resistor, what is the resistance in mega ohms? That's crucial there too, mega ohms. So the first band is red, and you can see from my circles down there, this column gives us the first digit of the resistance. The second band gives us the second digit of the resistance. The third band gives us the multiplier. And then the fourth band gives us the tolerance, so the uncertainty. So our first band is red, which means our first digit is 2. The second band is brown, so the second digit is 1. The third band is gray, so that's a multiplier. I don't know why he did that with the commas. It's gross. But anyway, if you count the zeros, 1, 2, 3, 4, 5, 6, 7, 8. So I think that's 8. Anyway, there's our multiplier, and so we end up with a resistance of 210 mega ohms, because this is our resistance in ohms. And mega is times 10 to the 6. Mega is million. So 210 million ohms. Okie dokie. The next one, this one I believe corresponds to experiment 5, because we have resistors in both series and parallel. I chose this version of the question because I think this one is the most complicated to look at. But I think there were 3 different versions of this. Anyway, he wants to know what the current value is at that location and what the voltage value is at that location. So let's think through our reasoning for this, right? When we're dealing with parallel circuits versus series circuits, they behave differently. So we've talked about that in terms of capacitance, but similar rules apply when you're talking about charge or voltage or current, resistance. Pretty much all of those quantities behave differently in series versus parallel circuits. So in a parallel circuit, which comes first here, the voltage that goes into each branch is equal, but the current is not necessarily equal through each branch. The current that goes through each branch depends on the resistance that's in that particular branch. And you may remember this with the light bulbs, how when we set up some of the circuits, some of the light bulbs were brighter than other light bulbs in the same circuit. So that's just because the amount of current that's flowing through that branch for a brighter light bulb would have more current, and for a dimmer light bulb would have less current because that light bulb has more resistance. So greater resistance means less current that's flowing through that branch. And then in a series circuit, the current is equal everywhere, but the voltage is not necessarily the same. It'll drop differently depending on the resistance that it is going across. So our total resistance in the circuit, since we have first that parallel chunk and then it goes into a series circuit after that, we have to kind of combine these 2 ideas, just like we did with capacitance in the earlier example. So in a parallel circuit, the resistance adds inversely. So 1 over R1 plus 1 over R2 plus 1 over R3 to the negative 1, the inverse of that, plus R4. So when we go through and do that math, since all of our resistances in this parallel part are 20 ohms, when we add 1 over 20 plus 1 over 20 plus 1 over 20, we get 3 over 20. So 3 over 20 inverse plus our fourth resistor is 10 ohms. So the inverse of 3 over 20 plus 10 is 16.67 ohms. Of course, that's not the answer he's looking for. He's looking for the current and the voltage, not the resistance. But we need that resistance to find the current and the voltage using Ohm's law. So Ohm's law states V equals IR, voltage equals current times resistance. And so current equals voltage divided by resistance. In this case, we're looking for the total current for now. So total current equals total voltage over total resistance. So our total voltage from the battery is 20 volts. Our total resistance we just calculated to be 16.67 ohms. That gives us a total current of 1.2 amps. And again, in a parallel circuit, this current is split between the branches. But since here all of our branches have the same amount of resistance, that means that our current is going to split evenly between the three branches. So 1.2 amps divided by 3 branches gives us 0.4 amps for each branch. So that's what the current is going to read through this bottom branch here is 0.4 amps. So now we need to find the voltage across our fourth resistor. And again, we're going to apply Ohm's law, but specifically in that place, not for the total circuit like we did up here. But it's the same equation, we just plug in the numbers that we're using. So the current that's flowing through our circuit is 1.2 amps because, remember, in a series circuit that we're dealing with now, the current is the same everywhere. So if there's 1.2 amps flowing into these parallel branches, there will be 1.2 amps flowing out of them total. And so there's 1.2 amps everywhere in the rest of the circuit. So our current is 1.2, our resistance is 10, and that gives us a magnitude of 12 volts. However, and this is another one of those tricky things where you have to make sure you're looking very carefully, this voltmeter is hooked up backwards. It has the black probe first and the red probe second. And it should be the other way around. We should have the red probe first and the black probe second. So you might remember if you actually did this in person, when you probe something backwards like that, you get a negative value instead of a positive value. So that's why the correct answer here is negative 12 volts, because the voltmeter is wired in there backwards. Okay, hopefully that makes sense. Again, I highly recommend that you go through your particular quiz question yourself, since yours might be different than this example, and just make sure that you understand the math behind it. If you don't understand it, if you have questions, let me know and I can help you work through the solution for that. Okay. Quiz 3 covered experiments 6 through 8. So that was the oscilloscope, RC circuits, and Earth's magnetic field. Just want to make sure that I'm not making that up. Yeah, RC circuit was experiment 7. So I wanted to spend some time going through these oscilloscope questions. I am assuming by now, especially if you were an in-person student, that you have more practice with an oscilloscope than you ever cared to have. So some of these questions might seem very obvious to you now that you've kind of worked with them more. But for those of you who didn't have this lab in person, you might be a little less familiar with the oscilloscope and the struggles that result. So I wanted to go through all of these questions that he gave you. So what he wants for these questions is to just use the number to say which knob or switch does a certain thing to your screen, your display. So he wants to know which one allows the user to control the sweep circuit with an external voltage signal instead of what's connected to channel 1 or channel 2. So this is going to be a trigger knob, a trig. If you remember playing around with those trig knobs, they kind of they allowed you to change the speed of the beam as it goes across the screen. So that's how you could like freeze an image on the screen if you got it to the correct place. Or if you turned it way down, you could see it just moving really, really slow. And so that was kind of entertaining sometimes. But anyway, it's going to be one of those trig knobs. And since we're dealing with an external voltage signal, that means we're going to use the external trig knob. So number 14. The channel 1 and channel 2 are connected to knob number 4, the trig level. So that's why the correct answer was not number 4, because the question specifically says the one that deals with an external voltage signal, and that's number 14. Which knob allows the user to shrink or expand the vertical axis scale on the screen? This was your volt div knobs. Remember, you could turn it, if you turned it all the way to the left, you got like really big voltages. And then if you turned it to the right, you would get like small volt div settings. So there are two knob 11s there, one for channel 1, one for channel 2, and they both allow you to adjust kind of the amplitude of your display. Okay, which one adjusts the voltage level that determines when the sweep circuit starts moving the electron beam across the screen? So again, since we're dealing with the sweep and the beam going across the screen, that's a trig level. And so this would be our knob number 4, the one connected to channel 1 or channel 2. Okay. Next one, which allows the user to change which input or combination of inputs are displayed on the screen. That would be number 12 here, where we can change from channel 1 to channel 2. Dual means both displayed kind of like overlapping each other, and add was you add the signals together to get a different wave or a different display. So that's knob, well, I guess it's not a knob, it's a switch 12. Which one can make a blurry trace appear sharp? That would be the focus up here, number 8. Which one allows for the display of a constant voltage offset added to an alternating voltage signal and figure out where 0 volts are? That would be switch number 2, where you can switch between alternating current, direct current, or ground. Ground would show you where your 0 level is. Which one allows you to select different inputs that would then control the sweep circuit? That's the key phrase here, that then control the sweep circuit. So that would be up here next to your trigger level, switch number 7. Which one moves the whole trace on the screen up or down? That would be your vertical position. So knobs number 3. Again, this one would correspond to channel 1, and this one corresponds to channel 2. Where do you plug the wires into? That would be jack 9 down there. How do you change the display from voltage versus time to voltage versus another voltage? And that is this XY button. So here we're kind of plotting input 1 versus input 2. I guess input 2 versus input 1, because channel 2 is your Y value and channel 1 is your X value. So if you remember when we were doing some of these oscilloscope experiments, we would plot the Lissajous figures, and to do that we would push in the XY button, so we're plotting one versus the other one, and it creates these really interesting, cool shapes. I know some students got to play around with that in person and make really, really cool designs. Others may not have been so ambitious to just play with the oscilloscopes, which is fine. Or you may not have been in person to mess around with it too much, which is also fine. But the Lisa Drew figures that you can create are very pretty. Also, when we were trying to find the resonant frequency in one of the later experiments, we pushed the XY button in so that we could plot them against each other and figure out the resonance frequency was where it made a 45-degree angle, a straight line. So that's what the XY button does for us. Which one allows the user to shrink or expand the horizontal axis scale on the screen? So that would be this time div knob. Lets you stretch it out really far, squish it together. Okay. So you can see there are a couple of knobs that we didn't talk about in these questions. So like number 6, which just lets you shift the image horizontally. The intensity, number 13, just makes it brighter or fainter. So a couple of knobs that we didn't talk about. Make sure that you know what each of them does. Here is an oscilloscope screen example. So it displays a 207 hertz alternating voltage signal, and he wants to know what the time div knob is set at for this. So yeah, I think the key to this one was realizing units are important, and it's important to know what units correspond to what quantities. So if you know that hertz is a unit of frequency, then that gives you kind of a clue as to where to start with this. So our frequency is 207 hertz, and if period is 1 over frequency, then the period is 1 over 207, or 0.00483 seconds. The period, since our x value in an oscilloscope is time, that means our period is the distance from like crest to crest or trough to trough. So the distance from a point on one wave to the same point on the next wave in the x direction, that's our period. And so he actually put it in a very convenient place. It crosses the axis right here at the origin. And so I chose that location and the same location on the previous wave. I did not choose this location because that is not the same point on the wave. Right here, if you look at it reading to the left, this is part of the down portion of the wave. And where it crosses this axis right here is part of the up portion of the wave, and that's not the same. So we need to go all the way over to where it's going down the wave again, crossing the axis, and that's right there. So the period is that x distance, which ends up being 1, 2, 2.5-ish boxes, or 2.5 divisions. And we basically want to know what one division is, what the volt div knob is set at. So we take our period that we calculated from the frequency. That equals 2.5 divisions. So that means one division is our period divided by 2.5, or 0.0019 seconds, which is approximately 2 milliseconds. So that's what our time div knob is set at. Okay, another reading an oscilloscope question. I will say that he does like to do questions where you look at a picture and then like take measurements off of that picture. So these, the last example and this one, I would say are good ones to make sure you understand. Anyway, a resistor and capacitor and signal generator are connected in series. And we want to know what the time constant is for this display here. So that would deal with experiment 7, the RC circuit. And he tells you in the concept section in this experiment that the time constant is the x value when the y value is at 63% of the peak-to-peak voltage. So let's figure out what the peak-to-peak voltage is. It starts all the way down here at this line, and its final height is 1, 2, 3, 4, 5, 6 divisions tall. So peak to peak is 6 divisions. We want 63% of that value, so 0.63 times 6 is 3.78 divisions. So we want to figure out where this line, the x value when this line has gone up 3.7 boxes, 3.78. So 1, 2, 3.78-ish. I just took that to be this convenient location of right where it's crossing the vertical line. And if you remember, reading an oscilloscope screen is notoriously difficult because it's just so inaccurate. So there is a little bit of wiggle room in these answers. But so I just took it to be where it crosses that line just for simplicity's sake. But anyway, we want the x value when the y value is 3.78. And so that would be 1, 2, 3 divisions over from our peak down here. So x is 3 divisions. It tells us that one knob is set to 10 milliseconds per division. So you need to remember that the x value is time. So that tells us our x division value. So each division is worth 10 milliseconds. So 3 divisions times 10 milliseconds per division gives us 30 milliseconds as our time constant. Whew. Okay. So again, from experiment 7, the RC circuit, we have a resistance value, a capacitance value, and we want the propagated absolute error in the time constant. So this was a little bit tricky because you had to know how to calculate the time constant from a resistance and a capacitance. It's actually very simple. It's just R times C, which is why it's called an RC circuit. So tau, our time constant, is R times C, which means we'll use error propagation for x times y from Appendix C. And here I'm going to go through those two different methods that you could use to calculate this. So method 1 is to propagate using those percents that were given, and then convert that answer to the absolute error. So if we do it that way, and we look at our table in Appendix C3 for x, y, we see our equation for x times y to be this right here. So we plug in our percents. Percent error in resistance squared is 10 squared. Percent error in capacitance squared is 20 squared. And so the square root of that gives us 22.36%. So to convert that from a percent error to an absolute error, we use this equation for percent error, which if you don't remember this from Physics 1 lab, it should be in Appendix I for you. But percent error is the uncertainty divided by the value times 100%. So if we rearrange that, that means the absolute error, sigma tau, is the percent times the value divided by 100. So 22.36 times the value, our tau is R times C, so R times C divided by 100, which gives you an absolute error of 0.59. So that's one method that you could use. Another method is to convert to absolute error first and then propagate those errors, like we did in the previous example. Although this equation is a little bit different than previously because we're not dealing with x plus y. Here we have x times y. So we have a different equation that we need to propagate through. But this equation is the square root of c squared times sigma r squared plus r squared times sigma c squared. So you plug in your capacitance and your uncertainty in the resistance, plug in your resistance and the uncertainty in the capacitance, and then you end up with the same answer of 0.59. So these lines up here are where I figured out those uncertainties, right? 10% of 120,000, 20% of 22 microfarads, micro is times 10 to the negative 6. Two different methods, same answer, pick your poison. All right, this one is experiment 8. We're dealing with the hiking compass, either above or below the coil of wires, and we want to know which direction the resultant magnetic field will be pointing in. So if you're dealing with the compass above the coil of wires, you'll get a different answer than if your compass is below the coil of wires. And so I went through both of these cases just so you can see the difference. But what we want to do here is use a right-hand rule. So we point our thumb in the direction that the current is flowing and curl your fingers around in the direction of the magnetic field. Your fingers can only curl one direction if your thumb is pointing a specific direction. I don't think anybody can actually like curl their fingers backwards that far. So this is a good method to figure out the direction of the magnetic field, right? So use your fingertips as your like position of the compass, right? So if my thumb is pointing in the direction of the current and the compass is on top of the wire, that means the field is pointing, if you actually do this along with me, it's pointing away from you. So towards the computer screen, which means that the magnetic field is pointing to the east. And since the Earth's magnetic field is aligned in the north direction, we combine those two directions. So north plus east gives us a resultant of northeast, which is quadrant 1. If the compass is below the coil of wires, well, now my fingers are pointing towards me or towards the west. So then our resultant field is north plus west or northwest. Okay, so I mean, nobody's going to watch you while you take your exam, so feel free to like make all these weird whatever you do for your right hand rule. Nobody's going to judge. Okay, also from experiment 8, Earth magnetic field, we have the Helmholtz coil, and the coil of wire, of course, generates its own magnetic field like we just saw. So in this case, if we curl our fingers in the direction of the current, then our thumb points in the direction of the magnetic field. So that's why it's going through the coils in a straight line like that. So the coils are creating a magnetic field, Earth is creating a magnetic field, those two are going to add together. And he's asking us to find the components of the total magnetic field. So we need to include both the field from the coil and the field from Earth. And so if we look in that experiment in the concept section, it tells us the magnitude of the Earth's magnetic field, which is 0.24 Gauss. And that's just in that north, pointing towards the north direction. So there's only the one component of that magnetic field. You can see, I'll calculate that specifically in just a minute. Also from the manual, equation 8.1 gives us the equation for the coil's magnetic field, which is K times I. K is a constant that was given to us in part 3, step 3, which was kind of tricky because he cut out part 3, so we didn't actually do that part, and yet this crucial bit of information was embedded in there. To make sure you read carefully, even the parts that we didn't perform in class this year. But K is 17 plus or minus 0.2 Gauss per amps. So we break down both of those fields into their components. The coil's x direction is K times I times the cosine of our angle, which in this case is a 36-degree angle. And the y component is K times I times sine of our angle. So you can see those broken out there. The Earth's magnetic field in the x direction, it tells us that 0 degrees is local magnetic north. So that's the field from Earth, which means its angle is 0 degrees. So BE times the cosine of 0 is just BE, which we were given is 0.24 Gauss. Yeah, 0.24. And then the y component is the sine of 0, which is 0. So our final answer then, we have to add the x components together and add the y components together. So there, that last line, you can see I'm adding together the x component from the coil and the Earth, and then the y components from the coil and the Earth. And so we get our final answer, the components of our total magnetic field. Okay, finally, quiz 4, our last 3 experiments. So in this case, we're dealing with a resistor and an inductor, and they're connected in series. So this corresponds to experiment 10, I believe. Let me just make sure. Yep, experiment 11 was RLC circuit. So experiment 10 was magnetic induction. Okay. And so in this case, we have a resistor that has a gold tolerance band, and the inductance has an uncertainty of plus or minus 10%. So now we need to do some error propagation and figure out the percent error in the time constant. So this combines several different things together. First of all, we need to use Appendix F to figure out what a gold tolerance band means. And if you look in that chart for resistors and their band colors, gold has a tolerance value of plus or minus 5%. We know the inductance value is plus or minus 10%. We'll use Appendix C as well for our error propagation formula, but we have to figure out which one to use, and that will depend on how we calculate the time constant using R and L. L is inductance. So experiment 10, part 3, step 3 gives us a hint as to how to do that. It doesn't tell you straight up how to do that. So if you read his hint, you should come to the conclusion that the time constant is L over R. So when we go to Appendix C, we're going to be dealing with the formulas for X over Y. And we're calculating a percent error. So we're going to use that equation all the way in the right-hand column. Percent sigma X squared plus percent sigma Y squared, take the square root of that. And so we get 10 squared plus 5 squared, take the square root. We end up with an answer of 11%. Okay, experiment 11, the RLC circuit experiment. Sinusoidal oscilloscope trace. It's important that it says sinusoidal oscilloscope trace. Has a 4.4 peak-to-peak division, and the oscilloscope is set at 1 volt per division. We have the resistance of the resistor as 6,875 ohms. We need to figure out the current amplitude. This question was so commonly missed. I ended up giving partial credit to almost everyone because almost everyone gave me the peak-to-peak amplitude of the current, not the current amplitude. Peak-to-peak amplitude and amplitude are not the same thing. Peak to peak deals with the bottom of the wave to the top of the wave. Amplitude is the midpoint of the wave to the top of the wave, or midpoint to bottom. Okay, so we'll need to keep that in mind later on in our calculations. But first we need to figure out what the peak to peak voltage is. 4.4 divisions times 1 volt per division gives us 4.4 volts. We can use Ohm's law then, now that we have the voltage and the resistance, to figure out the current, which ends up being 6.4 times 10 to the negative 4 amps. Or I put it into microamps because that's specifically what he asks for, 640 microamps. But again, that's the peak-to-peak amplitude, which is twice our normal amplitude. So we need to take half of that number, which is 320 microamps. So again, another tricky thing that he likes to throw in there to make sure you really know what you're talking about. Okay, here, this was experiment 12, the speed of sound. So if you were in class, you remember how we performed this experiment. There's a big long tube that was sitting on the floor. Of course, like only one microphone, maybe 2 microphones in the whole room worked. But we had a microphone at the top of the tube. You snap your fingers, the sound wave travels down the tube, hits the floor, bounces back up into the microphone. So the microphone detects the initial snap and the echo. And you can see that as 2 separate pulses in our graph. So that first wave pulse is your snap, the second wave pulse is the echo. So to figure out a speed of anything, it's distance traveled divided by the time that it travels. And in this case, the distance that it traveled is 2 times the length of the tube because it travels down and then back up. So our equation 12.1, the speed of sound, which is lowercase c, is twice that distance divided by the change in time, or the time interval. So we want to look at where that first wave pulse starts compared to where the second wave pulse starts. And so the first wave pulse starts at 11 milliseconds. The second wave pulse starts at 23 milliseconds. So 23 minus 11 is our time difference. Of course, that's in milliseconds, and we'll need it to be in seconds. So I convert it there in the equation. Okay, so twice our distance divided by that change in time gives us our answer of 330 meters per second. All right, another wave picture, not necessarily an oscilloscope, because this is again pertaining to experiment 12, where we had the standing waves in the string. It tells us that this string is 120 centimeters long. So that whole length is 120 centimeters. And really the reason why he tells you that is so that you have a reference as to how big these numbers on the bottom actually are. And in this picture, they're very hard to read. I apologize for that. But each one is like a factor of 10 smaller than it should be. Like this is 10, it should be 100. This is 12, it should be 120. And so that means that each of these little tiny boxes, they're very faint, but each grid line is 4 centimeters. So remember, wavelength is like your crest to crest distance or your trough to trough, same point on one wave to the same point on the next wave. And you have to be careful in this picture to follow just one wave form. So I chose this part just because it's conveniently at 0. And then if we follow that all the way around to where it crosses the axis again at the same point in the wave, we can see that is a value of, here's 40, 44, 48 is our correct answer. So 48 centimeters is the wavelength. All right, again, experiment 12. We have 2 values for the speed of sound. We have the theoretical and the experimental. So our theoretical is 339, and we need to figure out what our experimental value is. We know it's going to be 300 something, but we have to figure out what those other 2 digits are in order for these 2 speeds to just barely agree within the limits of experimental error. So when we're talking about agreement within the limits of experimental error, that means we're dealing with discrepancy versus error in discrepancy. So D versus sigma D comparison here. So our sigma D, which is the error in experimental squared plus the error in theoretical squared, square root, our errors are both 5, plus or minus 5. So we plug 5 into that equation and we get a result of 7-ish, 7.07. So that means that our answers, our acceptable answers, will be within 7, plus or minus 7, of our theoretical value. So 339 plus 7 is 346. 339 minus 7 is 332. And he then asked for just the last 2 digits of the experimental value. And a lot of students missed that key part, so Canvas marked them wrong. I then went back and made sure that you got credit for that, but be careful of those sorts of things. So he was looking for either 46 or 32, just those last 2 digits. Okay, here we have what should be a familiar shark fin curve. This is an inductor and resistor, so this would be experiment 10. And he wants you to choose a response that best completes the following sentence. So the tall, flat part at the top of the fin is because ... and then it was a multiple choice. So the correct answer to this is because the magnitude of the magnetic field in the inductor is no longer changing. And we can see that if we take the slope of this graph at each of the different points. So since we're dealing with the top part of our shark fin, it's pretty flat up there. The slope of a flat line, a flat horizontal line, is 0. So we know that the magnetic field is, the change in magnetic field is approaching 0. It's approaching a constant value. The other version of this question is asking about that steep upwardly sloped part at the beginning. What's happening there? And again, if we look at the slope of that line, we see that the slope is changing very quickly. It's very steep. And so the magnitude of the magnetic field is changing very rapidly because we have a steep slope there. Hopefully that makes sense, those two things. Whew, we made it. So do you guys have any questions about those quiz questions or any of the other questions or experiments, etc.? This is your chance now to ask me whatever questions you have. So again, you can...
Yeah, I just have one question on the first quiz for the capacitors. Reading the capacitor, like, so the example was 823H, but when I look at the appendix, it says the third digit is a multiplier. So I think it would be 82,000 instead of 82,300, but I don't know if I'm interpreting that wrong.
No, you're right. I think that's just a yes, you're right. Amanda, is this you talking?
Yeah.
Okay. Yeah, Amanda, you're right. I'll go back and fix that in the example. That was an oversight on my part. Good.
Thank you.
Yeah. So let me go back to the slide that she's referring to. That's quiz 2. Did I pass it? I passed it. This one. Okay. Yeah, so this right there. Right, this third digit, what she's referring to, is the multiplier. And we can see, if you look in Appendix F, it tells you all about that. So let me grab my calculator and fix this before I forget. But do you guys have any other questions or comments?
Is it possible for you to like just give a brief explanation of the different types of errors again?
Yeah. Okay. Let me just fix this real quick, and then I will, of course, answer that question for you. Amanda, I'm glad that you're here to fix my mistakes.
I hope it's not annoying.
No, it's not. It's very, very helpful. I mean, I am human. I do make mistakes as well. There's another one where I missed the units. Anyway, the types of error. So we have 4 different kinds of error, really, that we're dealing with in experiments. And so if you look in Appendix I, I'm sorry, Appendix H, I guess. Appendix H, which is the how-to lessons from Physics 1 Lab. It has a little, I'll try to hold it up for you since you might not have it open. But it has that little flow chart there, which is really helpful to look through. So it has two different branches initially. So you can either have intrinsic errors or you can have errors in measurement. So intrinsic errors are errors that are like built into the experiment that you can't necessarily control or minimize. And then errors in measurement are things that you could potentially minimize if you use like the correct equipment or if you calibrate it correctly, that sort of thing. And then we also have random errors versus systematic errors. So an error is a random error if it just affects one or two of your measurements, or if it doesn't affect them all in the same way. And a systematic error is one that affects all of your measurements in the same way. So if we have an intrinsic systematic error, that is an error that's built into your experiment that affects all of your measurements the same way. So that might be like this one, faulty equipment. The example that it gives in the manual, let me see if I can find it real quick. Friction, not including friction, right? That would affect all of your measurements, and friction is built into the world. You can't really control that. So if we ignore friction, that's a systematic intrinsic error. Intrinsic random error would be built into the experiment, but it doesn't affect all of your measurements the same way. So let's say your experiment is measuring your heart rate. Well, I can just be sitting here doing nothing, and if I take my pulse at like right now and then wait like a minute and then take it again, it may not be the same. So that would be intrinsic because my heart rate is built into me, and random because it won't affect all of my measurements the same way. Like if I change my breathing or whatever, that's the example that he gives for intrinsic random error. Then we have our errors in measurement. So systematic error in measurement would be something like an uncalibrated equipment where you could have calibrated it, but you didn't. And so now that uncalibration affects all of your measurements the same way, but it was something that you could have changed. And then random error in measurement doesn't affect all of your measurements the same way, but you could have changed it if you had used a different measuring device. So let's say you want to measure the length of something, but you're using a yardstick that only has centimeters versus a yardstick that has millimeters. If you use millimeters, you can kind of minimize that error a little bit more, but there's still going to be random error in measurement because you still have to eyeball that distance. And so anytime we're dealing with human error, we like to call it, that's a random error in measurement. If you're using a stopwatch, your reaction time is a random error in measurement because that won't necessarily affect all of your measurements the same way. Does that make sense?
Yes, thank you.
Okay, great. Any other questions that you guys have? All right. Well, of course, if you guys do have questions later on today, you're welcome to send me an email and I'll answer to the best of my abilities. I will, again, try to look through what questions I can on your exam, and hopefully give you guys some hints, some tips on how to use your time the most wisely. But If you look in your manual, Appendix E is all about the final exam and potential topics that could be covered. So definitely take a look at that list of topics. I would say be prepared for error propagation for sure. Nothing crazier than what we went through in these examples, or what you did in the experiments. So error propagation for sure. Classifying errors, he really likes to do those. Be familiar with the oscilloscope, what all of those knobs do. He likes to do questions based off of pictures. So, be familiar with reading an oscilloscope screen, what the Y direction means, what the X direction means, how to read a period versus a wavelength versus a peak-to-peak voltage, those sorts of things. I can almost guarantee that he'll have some questions based off of pictures. Make sure you know the rules for circuits, series versus parallel. So for things like current, resistance, voltage, charge, capacitance, how all of those things work in series versus parallel. Make yourself a little cheat sheet for those. That might help you save time and sanity on the test. Make sure you review Appendix F, those resistor color codes, the capacitance codes, because I make mistakes too. The tolerances of your multimeter, all of that can be found in Appendix F. So make sure you're familiar with that. And then he will most likely have conceptual questions from the experiments as well. So don't neglect reading through the concept sections. I know some people, they just like to skip right to the procedure in class, especially this semester because we were pressed for time. But there's a lot of really good information in the concept section that is fair game for him to ask you about. So yeah, those are my general tips for you. And I wish you guys the best of luck. Remember, your exam is tomorrow morning from 10:30 to 12:30, unless you get extended time, in which case it's 8:30 to 12:30. And those times are Eastern Standard Time, so Melbourne time. Yeah, I hope you guys do well. And I will be going through all of the questions myself, even the ones that are automatically graded by Canvas, because we all know Canvas makes mistakes. So your grades will be finalized by the end of final exam week. And then, yeah, if you have individual questions about any of your work, then you can send me an email. Good deal? All right, good deal. Well, I will stop this recording then, and I will stick around for a couple minutes if you guys have specific questions. But I know we're already past our allotted time. So I hope you guys have a great day. Good luck studying and good luck on your exam.
Thank
Bye.
you for hosting the review.